So, last class I was discussing about one example problem, where H section steel pile was taken and the soil properties were given, and there are two soil conditions were given. One is the granular soil, another is the clayey soil, and the diameter or the size of the section was 250 millimeters. So, diameter was taken 250 millimeter as the size was given. So, these values are available for a particular section, and this for this chosen section these are the values. So, and this is D value is 250 millimeter, L value is 220 meter. So, L by D is 80. So, it's a long pile, definitely it will be a long pile. So, we have to determine what would be the value of yield stress, yield moments, because yield stress is given. So, based on that you have to calculate the yield moment. So, water table at the 2 point below the ground surface, and then moment of inertia about the x axis, d1, d2 value, thickness of the wave and the flange. So, all are given. So, now we will get the yield moment. So, yield moment is equal to S and Fy. What is Fy? Fy is the yield stress and S is section modulus. Most of the cases these yield stress are given and section modulus is given. So, we have to calculate the yield moment. Directly yield moment will not be given, but if the directly yield moment is given, then you can use that yield moment directly. But most of the cases the yield stress and the section modulus that is given. So, for the section modulus, how we can get that? So, yield stress is given, that is 340 mega Newton per meter square. So, section modulus S is equal to I x x divided by d12. So, d12 by 2, that means the half. So, that is this particular case, this particular section, the section modulus is this. So, section modulus I x s is given 87.5 into 10 to the power minus 6, and this is d by 2. So, this will be 2 and d1 is how much? d1 is 0.246. Okay. So, this is the section modulus. So, m y will be S into F y. So, S is 87.5 into 10 to the power minus 6 into 2 divided by 0.246. F y is equal to 340. It is given as mega Newton. So, we are converting it to kilonewton. So, this will be 10 to the power 3. So, this value is 242 kilonewton meter. So, yield moment for this particular section is 242 kilonewton per meter. Okay. Now, for different sections, what would be the section modulus? So, quickly I am giving that idea, because this is a H pile section, but suppose if it is a circular section, then the section modulus will be, so suppose the circular section of diameter d, then the section modulus will be I x x. So, this will be pi d to the power 4 by 64 divided by d by 2. Okay. So, this will be pi d cube by 32 for the circular section. Now, if it is a rectangular section, if this is B and this is H, then the section modulus will be what? B h cube divided by 2, 12 divided by h by 2. Okay, because this is the x axis, and now this is y axis. So, for a circular section it is the symmetric case. So, this will be b h to the power b h to the power square divided by 6. Yes. Now, the last section that is the hollow circular section, say what will be the section modulus. So, this is d 2 and the inner one is say d 1. So, S will be pi d 2 to the power 4 to the power d 1 to the power 4 divided by 64 divided by d 2 by 2. Okay. So, for this case S will be pi 32 d to the power 4 minus d 1 to the power 4 divided by d 2. So, these are the section moduluses for different section. These are section modulus for different section. Now, for our case we have determined the MY value and that value is 242 kilonewton meter, and where the different section each section where section modulus is we have determined by using these equations, and the same equations we have used for these particular sections and we have determined their section modulus. Now, first we will consider the Brom's approach. And the first case is the granular soil. Or I should say that I should write the granular soil first, then for the granular soil first one will be the Brom's approach and then next second one will be the simplified approach. Okay. Now, it is a free headed pile with E is equal to 0, because E is given 0 here, E is 0, free headed pile, but E is 0. So, for this particular case either we can use those equations, but I will use the charts, because those charts are developed based on the those equations, where it is a cohesive soil first case it is a granular soil. So, it will be the cohesionless soil and it is a long pile, okay. Long pile, and so we know the yield moment. So, we have to calculate M yield Kp gamma dash d4. So, let us calculate that. So, you have to calculate M yield Kp gamma dash d4. Now, which gamma we will consider, because the gamma is given that is 2 millimeter below the ground. So, if this is the ground surface and H is acting here, HU, because it is E is 0 and water table is here, which is 2 meter, and rest of the pile is 18 meter. The total is 20 meter, and 18 meter below the water table and 2 meter above the water table. So, here I have taken the weighted average unit weight, and so that means that it will be 18 into 2 plus 20 minus 10 into 18 divided by 20. Okay. So, unit weight of water is taken as, okay, it is not given. So, unit weight of water is taken as kilonewton per meter cube, and submerged unit weight is water table below unit weight below water table and 20 kilonewton per meter cube, it is a submerged, it is a saturated unit weight. So, this is definitely this will be a saturated unit weight. gamma sat, because it is 20 kilonewton per meter cube. Submerged cannot be 20 kilonewton per meter cube. Submerged will be 20 minus 10, 10 kilonewton per meter cube, or close to 10 kilonewton per meter cube. So, that means here we have taken the weighted average 18 into 2 plus 20 minus 10 into 18 divided by 20. If the water table is at the ground surface, then directly we can calculate, we can use the gamma dash is equal to 10 kilonewton per meter cube, if it is a ground surface. If it is not ground surface, that is why you have taken the weighted average value, and that value is 10.8 kilonewton per meter cube, and Kp is equal to 1 plus sin phi divided by 1 minus sin phi. So, this will be 1 minus sin phi value is 40 degree. So, 1 minus sin 40 degree, 1 plus sin 1 plus 40 degree. So, this will be minus passive earth pressure coefficient. So, this is equal to 4.6. Okay. Now, I will put these values here. So, the yield moment is how much? 242, 242, then Kp is 4.6, unit weight is 10.8, diameter is 0.25 to the power 4. So, this is 1247. Okay. Now, let us go to that chart, and L by D is equal to 80. So, let us go to this chart. This is for the cohesionless soil or granular soil, long pile. So, this value is 1247. So, this will be somewhere here, and the L by D, this is E by D is equal to 0. So, this value will be somewhere here. So, from here I can take the value which is this is 1247. So, 1247 will be, remember that this is in log scale. Okay. So, 1247 will be somewhere here, 1247, and this is the value, corresponding value is here, which is roughly 120. Okay. So, this is say 1247. So, roughly this value is 120. So, the value that we are getting, that HU Kp d cube gamma dash is 120 from the chart. So, that means corresponding HU Kp gamma dash, here I am using gamma bar d cube is equal to 120, because that is the value. HU divided by Kp d cube gamma dash. Here in place of gamma dash we are using gamma bar. So, HU will be equal to 120 into 4.6 into 10.8 into 0.25 to the power cube. So, this is 93.2 kilonewton. Okay. So, this is 93.2 kilonewton. Now, if I use the simplified approach, then this is the granular soil, so variation will be linear. So, in that case Pu bar will be PL divided by 2, and PL is nothing but 3 sigma V bar Kp divided by 2. Okay. And that sigma V you have to calculate at Z equal to L. So, what is sigma V bar at Z equal to L? So, sigma V bar at Z equal to L will be how much? So, sigma b bar will be 2 into 18 plus 20 minus 10 into 18. This is sigma b bar, okay, and PL is 3 into sigma b dash Kp. So, now if I calculate Pu bar, so I will get 3 divided by 2 sigma b bar 2 into 18 plus 20 minus 10 into 18 and Kp is 4.6. Okay. So, this value is equal to 1490.4 kilonewton meter square. So, Pu bar is 3 by 2 sigma b dash we have calculated into Kp 4.6. So, 1490.4. So, corresponding, so this is the linear variation, this curve, and E by L equal to 0, this value. So, Hu Pu bar dl is equal to 0.25. Okay. So, this is 0.25. So, I can get here the value corresponding Hu P bar dl is equal to 0.25. Okay. So, you can see this, there is a linear variation and the uniform, and the granular soil, this is the linear variation. So, this value is 0.25. So, once we put this value, so I will get that Hu is equal to 0.25 and Pu bar is equal to 1490.4, then dl is 0.25, dl is 20. So, this value 1863 kilonewton. So, Brom's approach is given a value which is 93.2 kilonewton, but the simplified approach is given a very higher value. So, that is why I would recommend that you use this Brom's approach, because it is giving lower value to be in the safer side. So, that means simplified approach, as I discussed, it is a linear variation. So, it is a linear variation. So, this is PL. So, my Pu bar will be equal to half into PL. So, that is the case, and PL is nothing but sigma b bar at we have to calculate at z equal to L, that we have calculated, that means at the pile tip, and then we put this equation and we will get the Pu bar value is like that 1490.4. Okay. So, now we will go for the second case, that is for the cohesive soil. So, previous one is for the granular soil and this is cohesive soil. So, by Brom's approach, so for Brom's approach, so this is the equation. So, and it is a long pile. So, these we have to calculate MY Cu d cube. So, here by Brom's approach, that MY Cu d cube. So, MY is 242 and Cu value is 100 kPa, d cube is 0.25 cube. So, this is 155. So, corresponding what value I will get from the chart. So, this is chart, this is Hu Cu d square. So, corresponding Hu Cu d square, that is coming how much, because this is 155. So, this is 155 will be somehow here, and then this is free aided is equal to 1. So, this will be here. So, it will be around 40, 45 around. This is 200 sorry 155. So, 155 means this is 155 mean log scale, this is 2, 3, 4, 5 somehow here. So, if I extend that, so it will be around here, around here. Okay. So, this value will be around 45, 46. So, I have taken this value is 45. So, this is 45. Okay. Remember one thing, that when you are taking some value from the chart, so that may change depending upon the person who is taking that value, slightly there may be a variation. So, this type of problem for the assignments. So, I will try to give these values directly, or I will give the equations, you have to use the equations. So, that there will not be any difference between the results of different persons. So, that means here this is 45. So, I can write that H u will be equal to 45 into 100 into 0.25 square. So, this is 281.3 kilonewton. Now, by simplified approach, again simplified approach, this is the chart uniform, because it is a now cohesive soil uniform. So, this value will be around, this is E equal to 0. So, this value is around 0.41. Okay. This is 0.41. So, this is H u by P u dash d L is equal to 0.41. So, now P u bar for granular soil is 9 Cu. Okay. So, this is 9 Cu. So, that why it is 9 into 100, this is 900 kilonewton meter square. Okay. So, H u will be 0.41 into 900 into 0.25 into 20. So, this is 1845 kilonewton, again higher than the Brahms approach. So, this way we can calculate the ultimate lateral load capacity of a pile depending upon its fixity condition, whether it is a free end or the fixed end, or it is within the granular soil or the cohesive soil. So, for the Brahms approach, either you can use the equations that I have given, or you can use the charts, okay, because those charts are developed by the those equations, okay, or either you can use the simplified approach, but I would recommend that you use the Brahms approach to determine the ultimate lateral load carrying capacity of the pile. So, now next class I will start the settlement response of the lateral loaded pile, because this section I have discussed the ultimate load carrying capacity of the lateral loaded pile. So, next class I will start the settlement response of the lateral loaded pile, and then I will discuss that how you can determine the settlement response of the pile, single pile as well as the group pile. And one more thing before I finish this today's lecture, that the group pile capacity for ultimate lateral load carrying capacity of group pile, because I have discussed all the single piles. So, group pile capacity is the same as we are using the same approach, but only in that case the diameter will be the width of the group, okay, or equivalent diameter of that group. Okay, so, that because we have done it for the pile under compressive load, how to calculate the width of a group. Okay, so, that width we can use for or we can take a equivalent area or equivalent diameter of the, or that in that rectangular or the square section we can convert to a equivalent circular section, then you will get a equivalent diameter of that group. So, that diameter also we can use. Then once you get that diameter, so then it will be a single pipe analysis. Okay. That means, that group section you convert it to equivalent circular section, then you determine the equivalent diameter, then after that the analysis is same, okay, for the group section that I have discussed for the single pile. So, in the next class I will discuss the settlement response of the pile, and then I will give you in the next week that how we can generate the simplified or the generalized PY curve for the lateral loaded pile. Thank you.